Now you can start.
Okay, thank you. Maybe before I start, I'm very happy to answer any questions you have. So please feel free to interrupt me anytime you want, especially if you can't read my handwriting. So I want to start with some conjecture. That was some of the driving conjecture in differential topology for the last 120 years, maybe the Poincaré conjecture. And it's big enough. And so the conjecture is about understanding the sphere. But we remind you of the spheres. And a set of points in R and plus one from the origin. Actually, dimension two. Yes, people try to understand this space. And what's special about this space is the first example of the so-called topological manifold. So topological manifold. I guess you all know what that means. And if you don't, a good approximation that might be good enough for here is saying it's a space that looks locally like that. Locally. And it is the same as R. That's not quite true, but it should be sufficient. And actually, it is more. It is also a smooth manifold. Smooth manifold is a topological manifold together with a smooth structure. I won't tell you what it is, but I hope that you know it. So it somehow means, roughly speaking, that you can do analysis on this space, that you know what the differential is, that you can measure lengths and stuff like this. It's maybe more surprising that there are manifolds that don't have smooth structures. It was known for a long time. And the point is that those manifolds that are topological manifolds without having smooth structures, that's something you can't describe easily. And so here's an example. I have this key. See this as a subspace of RC, and it has these corners here. So it's not a smooth submanifold. Yeah, but of course, this is homeomorphic. We just get this here. Now, this is my notation for homeomorphism. And then this has a smooth structure, and then you can use this homeomorphism to transport that smooth structure to that space. So that's a manifold which has a smooth structure. It's not a smooth submanifold, but abstractly you can put a smooth structure on it. And that process is called smoothing the corners. Yeah, so whenever you have some topological manifold that has corners, it's no problem at all. It has a smooth structure because it's homeomorphic to something with a smooth structure. Yeah, so in other words, whenever you have something which is not a smooth manifold, it has to come from some very weird limit process that you can't visualize easily. But nevertheless, those objects exist. And so now the question is, can we recognize this here among manifolds, smooth or topological manifolds? And what do I mean by this? I mean, let me first write the rough version of the conjecture. It's from something around 1900. And Poincaré asked the following question. Yeah, so let's assume we have a manifold of dimension n, and let's assume that it's closed and connected. So closed just means it's compact without any boundary, and n means it has dimension n. And then the conjecture asks if the algebraic topology of n is the same as the algebraic topology of Sn, are the spaces the same? So if the algebraic topology of n equals the algebraic topology of the sphere in the same dimension, then the question is m discrete Sn? Yeah, so it's a very unprecise statement, and maybe let's try to make it more precise. It's first saying what does this mean, and then saying what does this mean. Yeah, so what does the same algebraic topology mean? The same algebraic topology just means that the spaces are homomorphic. Yeah, so the precise version is this. Yeah, if m is homotopy equivalent to Sn. So this is my symbol for homotopy equivalence. And like this is, by the way, equivalent. Why is this the same as having the same algebraic topology? By combined work of algebraic topology of 50 years. This is equivalent to having the same fundamental group and the same homology. I want trivial and the homology M0 for k equal 2 up to n minus. Yeah, so this equivalence from here to here is like combining Hurewicz theorem with Whitehead theorem. Yeah, so saying that the space is homotopy equivalent to Sn is the same as saying it's trivial fundamental group and trivial homology groups. And then the question, does this imply that M is homeomorphic to Sn? Yeah, this is my notation for the existing homeomorphism between those spaces. And you could ask a refined question saying, is then M homomorphic to Sn? And then of course you would need to assume that it has a smooth structure.
Yeah. Could you brush up my memory? Because why are those two statements? If they are homomorphic,
you mean from here to here? You need to combine the Whitehead theorem with Hurewicz theorem.
That says like given a map that induces.
Yeah, so here, so you need to describe. So first you say, okay, if this is a fulfilled, then you use Hurewicz to show that the homotopy groups are all trivial. And then you can somehow write down a stupid map by saying I collapse, I have a point, a disk to a disk, and then I collapse all the rest to a point.
Okay,
I mean, it's really like, this is a lot of algebraic topology in this. I mean, so if you go to the headshot, there's a corollary saying exactly this, and it uses the whole book more. So I mean, it's known, but it's like kind of difficult algebraic topology. Does this answer the question partially?
Yeah, so the ingredient where you said that you have to construct this map beside it.
Yeah.
No,
I mean, I also don't know exactly, but I think something like this works. You know that? No.
Well, I mean, the map that you described clearly then induces isomorphisms on homology groups.
Yeah, so it should work.
That's fine.
Other questions about it? Yeah, so this is the Poincaré conjecture, and maybe let's discuss what is known about this. Yeah, it's known that this is true in the topological category. Yeah, so whenever you have this manifold that is homotopy equivalent to Sn, then it's actually homomorphic to Sn. And that is a combined work of several people. So for n equal 1 and 2, it's not too hard to do that. And for n equal 1, there's just one manifold, which is this here. That's trivial. For n equal 2, you can classify all two manifolds. Then you also get that result. For n equals 3, it's much harder. That's the result by Perelman from 2003. And it was offered the fields method. So that's a difficult result. And in n equal 4, it's also true. That's due to Friedland. And that's from 81. It was also awarded the fields level. And in higher it's also true. And due to several people, and I think the main input is a result by from also a fields level. And then, I mean, Snell's proved a slightly weaker result, but then people later figured out to get the whole thing. And in the smooth category, in dimension 1, 2, and 3, it is true, because there are manifolds that unique smooth structures. So there's a result by Moyes in the 50s, saying that if you have a topological form, it's n manifold where n is at most 3, then this manifold carries a unique smooth structure. The question is just the same. And then there's this big shock maybe in dimension 7. It's just wrong. That's the result by Milner. From 56. And he proved that there exists a manifold, a smooth manifold, which is 7-dimensional, that is homeomorphic to S7, but not diffeomorphic to S7. This dimension is just wrong. And more or less the proof methods of Milner and Snail combined give you very good understanding for the Poincare, smooth Poincare conjecture in high dimensions, bigger than 5. Now let me write here well understood. Yeah, I should warn you that well understood doesn't mean it's solved. There are actually infinitely many dimensions where it's unknown, but at least you have like very good, you can reduce it to algebra, say, and sometimes you can solve the algebra. For example, you know that in higher dimensions bigger than 5, there are at most finitely many exotic spheres. So many spheres that are homeomorphic to a sphere but not different. In every dimension 5. And in some dimensions it's just 2. I think in dimension 5 there's a unique smooth structure. In some other dimensions it's 4. In dimension 7 you can actually exactly say how many there are, 28. But then maybe you have noticed that dimension 4 I left open. And there's a reason that dimension 4 is totally unknown. I have no idea what's happening there. And also here, this dimension 4 proof is the weirdest result I ever saw. I mean, the proof makes no sense to me that this is working, but it is working, and here people have no idea why it's working, or if it's working at all. And well, the idea of this talk is to focus on dimension 4 mostly, and try to explain some methods that might help to prove or disprove it. And it will turn out that we can reduce these questions often to 3-dimensional questions that are very easy to state and then maybe hard to solve. Yeah. But are there any questions about this? Maybe let me state another strange result in dimension 4. I mean, this is like not a result, it's just unknown, but here's a very strange result that really tells that dimension 4 behaves completely different than all other dimensions. It's a theorem due to several people. It's Friedman again, then Taubes and Stalin. Yeah, the result is the following: that on Rn there exists a unique smooth structure. That's the meaning. What it means that if I have a smooth manifold N and smooth such that N is homeomorphic to Rn, then it is also differential. Just that this result is not true, it's just true in dimension not 4. And it's not equal to 4. Then this is true.
Your N looks like a 4.
This is my N, this is my 4. It's different topology. So, I don't know. So this is a 4, this is an N, this is a 4. It's the same for you. So I mean, I agree that my handwriting is horrible, but this I can distinguish. I mean, anyway, for the level of the talk, N will be 4, so it will not matter too much. Yeah, so on R4, there's a different result. On R4, there exist actually exotic smooth structures, and even worse, there exist uncountably many exotic smooth structures. There exist uncountably many smooth structures. Yeah, so that means, yeah, there is, that means there exist uncountably many manifolds that are all homeomorphic to R4, but pairwise non-differential.
Is there sort of a nice classification of these things, or is it just like, okay, you can do this trick with input this, and they're all different?
Yeah. I mean, there are results like
It's not like you can parameterize them.
I mean, there is like nice results saying something like exist in universal exotic R4. I think in some way exactly how this works. But I guess every exotic R4 embeds into it. Something like this is not okay. So it's
And what is known about the, because then you have some sort of kind of maybe order or partial order of like which one sit inside the others. I mean, how much do we know about this?
I don't know anything, but people know something. Maybe I'm the wrong person to ask.
Okay.
So what I will maybe convince you of is that there exists one exotic R4, not uncountably many. The uncountably many part is a bit harder, but there exists one is something which one can explain. That's one of the goals of the law, to prove this part without the uncountably many. And then a similar strategy might work actually to also disprove this, the Poincare conjecture in dimension 4. There I don't know how to do it, but there's at least a strategy to reduce it to a three-dimensional problem and then find knots with certain properties, and I would call exotic knot traces. That's the title of the talk. There's another question.
Yeah, I don't know if it's important for record, but when you say there's a unique smooth structure, they say, okay, if they're homomorphic, then they're also diffeomorphic. Does that mean that the map that gives homeomorphism is already a diffeomorphism, or can you make it into a diffeomorphism?
No, that doesn't mean that. No, I mean, I can even on R4, right? I can on R, right? I can find a homeomorphism that is not a diffeomorphism. No, that just means that abstractly is the diffeomorphism. So this symbol here means there exists diffeomorphism. That has nothing to do with this homeomorphism. I mean, one could ask if the homeomorphism is isotopic to diffeomorphism. I don't know the answer. That might be true. Other questions about this? Other questions?
So you say that global statements about R4.
Say it again.
Statements about R4, are they global or local? I mean, is reading the global diffeomorphism or
Well, they're smooth port manifolds, so they're locally diffeomorphic. That's what you're asking.
yeah.
Yeah, I mean, they're always
I mean, and you talk, the first part we talked about the sphere, so that's really like this. So to what extent is R4 like this in your?
maybe you're asking if what happens if I do the one-point complexity.
Yeah.
Then they all get standard. I mean, for example, there's one result, like if you have a closed four manifold, it might not have any smooth structure. But then if you remove a point, it has smooth structure. So it's not too easy to go from here to the mostly. Maybe that was the question.
Yeah. So I mean, that part is about the sphere, and that part is about.
Yeah. So here it's just saying there's dimension 4 is really behaving different than other dimensions, and that might be that here is also something completely different happening. That's one of the reasons why. Also, like this proof here in dimension 4, it's really like kind of different from the other dimension. Also, dimension 3, it's really different from higher dimensions. And then here you also see that like the dimension is high enough, it's just wrong. And in dimension 4 might be everything happening. It might also be that there are infinitely many smooth structure on S4. In all other dimensions, it's known that there are most finitely many. So I guess there's a statement that's known for four manifolds. If you have a four manifold where all smooth structures are classified, then it's either 0 or infinity. So that might be true in general, or might be both. At least there's no counter in something. Does that answer the question? Okay, then yeah, so to understand those results, or in general four manifold, one needs ways to build interesting four manifolds. And so the four manifold should be easy enough that we can understand them quite well, but complicated enough to have like this general exotic phenomena. And one way to do to study such manifolds is via knots in S3. So these are the so-called knot traces. So let me recall what a knot is. And so let's play in S3 be a knot. And so what do I mean with that? Yeah, a knot is the isotropy class of a smooth embedding of S1 into S3, or in general in any S3 manifold. And so this is my notation for a smooth embedding. And then I consider this smooth embedding up to isotropy. And I can also abuse notation slightly and see this, the image of this as a sub-one-dimensional submanifold in here. That's why I write substitute. Here are some examples. Now, this is the unknot of the round circle. And there's the trapole knot. This one. And then the next complicated, the figure 8 knot. See if I can do that. This. Figure 8 knot. Yeah, so what are these pictures here? I have drawn the images of such embeddings. And you can think of it like lying flat on the blackboard. And just at this point where I've interrupted it, I go a bit behind the blackboard, go under the other crossing, and then up it. And this uniquely defines me an isotropy class of an embedding of S1 into S. And these are the first three knots. I mean, the unknot is characterized by the property that it bounds a disk. And those I claim are not the unknot. Maybe obvious to see, and maybe a bit harder to prove.
These pictures, you picture yourself those in R3, so S3 minus a point, or really on S3?
Ah, yeah. I'm considering S3 as the 1 point compactification of S3. And because this is a compact set, and this is a smooth map, I miss a point, I remove that point, and then it's the same as working in R3 and S3. And then knot theory is a very interesting topic for itself, and people do that for a living. But I think it's really also a very nice way to study 3 and 4 manifolds. And so you can either use knots as a way to build new 3 and 4 manifolds, or you can use it really to study 3 and 4 manifolds, or both at the same time. And here's the construction. To construct one construction, there are several. This one construction is called the knot trace. You construct a knot, any of those or any other as complicated knot as you wish. And you can construct a 4 manifold out of this. It's called the knot trace. And you do the following. So you start with the 4 board, E4, and you attach a 2-handle to it. A 2-handle is a copy of E2 times E2. And I attach it to the gluing map 5. And 5 is a map from the boundary, from the first boundary here, there E2 times E2. It's an embedding into the boundary of E4. Smooth embedding. As I choose such a map, and with the property, and there are of course like infinitely many such maps, but I wanted such that the span, del D2 times 0, maps to the knot. Okay. So I start with a given knot, okay. The knot I see now as a knot in the boundary of D3, D4, which is an S3. And I want this solid torus to map this the core of the solid torus to the knot here. So let me draw a picture before I go on. I mean, not a picture, but just a sketch of what is happening. And for some people this helps, and for some people it doesn't help at all. So this is my 4 board, E4. Imagine E4 board as a two disks. And then I have in the boundary my knot. Yeah, I draw my knot now as an S0. In the boundary S1, this is my knot K. And then I attach this two handle, D2 times D2. And here I draw this D2 times D2 as D1 times D1, so as a cylinder, or as a spread. And I attach that along the first boundary times the tubular neighborhood of two. This is my sketch of a knot trace. And so maybe I should tell you this is not quite correct what I wrote so far, because there are now, I want to denote this manifold by W. And I want that this manifold just depends on the isotropy class of K. And that's at the moment not true, because here I have infinitely many choices to choose such a net phi. Because the point is like, this is really just the same as saying, this is a trivialization of the normal bundle of K. I choose an identification of del D2 of the solid torus with the tubular neighborhood. So I say here, and in reality, the tubular neighborhood sitting inside. And there are infinitely many choices, so I need to fix one choice. And there's one natural way to do that by saying that del D2 times 1 maps to a certain parallel copy of the longitude with the property that it is non-homologous in H1 of S3 minus K. Yeah, so I have an example. I have here my knot, okay, and then in there I find the lambda, the parallel copy of the knot, which is this one, which bounds at this in the knot complement. So it's null homologous. So then I choose an embedding phi that sends the solid torus to a tubular neighborhood of K, such that this curve gets mapped to the lambda. And then one can use a bit of homology theory to show that this lambda is actually unique up to isotropy, and then that this four manifold is unique up to diffeomorphism. It just depends on the knot. And so here in the picture, the longitude of the parallel knot is not lambda here. I don't know if this picture makes sense to you, but for me it helps. Is this construction very clear?
Can you draw this for the trefoil with the blue thing?
It's a bit more complicated. So let's try. Maybe let me just draw first the blackboard parallel. This one. This is not the zero longitude. One can check it's not null homologous. And then one can remember what the homology of the complement of the knot is. It's that generated by a meridian. And this class is actually the linking number of the knot. You know what that means. So you need to count now how many self-intersections I have of the blue knot with how many intersections I have of the blue knot with the white knot. So I orient everything in the same direction. And the blue knot in the same direction. And then I count here that it's actually three crossings. So it actually represents 3 in this group. So I need to add 3 negative twists to make it to 0. So let's try it here. 3 negative twists over, under, it was 1, over, under, 2, over, under, 3. So that should be the 0 longitude of the trefoil. And the same method works in any knot diagram. Does that make sense?
Why is this called a trace?
Yeah, so somehow and think of this as you have the knot, it's a 3-dimensional creature, and it leaves some object behind in 4-dimensional space. You've got that object that leaves it behind the trace. And it also tells you what you want to do with the trace. So it tells you, the question is, can you recover from the trace the knot? Can you put some object in 4-dimensional space, and you want to see which 3-dimensional creature left that space behind?
And then for the trefoil,
Yeah.
how would you explain this rotating 3 times around to describe the trace?
I mean, this has nothing to do with the trace. This is just a way to construct the trace. And you can also, and I should say this trace, you can also call 0 trace, You can do the same construction with any longitude here. It doesn't need to be 0. It can be 5 times the meridian, 100 times the meridian. You just have a different trace. It just turns out that if you choose 0 here, it's related to this problem and to this problem. And if you choose a general number there, it's not as good related. So this is just a choice I make. And at the moment, you could choose here any fixed number you want. And that would be a nice object to study. And people study that actually. It's just not as closely related to four-manifold topology as the 0 trace.
But trace is sort of a red herring in the sense that it has nothing to do with some trace of some linear map or something like this.
Okay. It's really I mean, I would say this trace has nothing to do with your trace, has nothing to do with the real trace.
Are those theorems that people studied defining or have started defining map traces or?
Yeah, so I mean, at the beginning, I think it's really a way to define interesting formulas. And then later they realized, okay, you can actually do like amazing things with those knot traces. For example, when people got more and more interested and they tried to study this more and more. And I mean, also this is also interesting from a three-dimensional viewpoint, because you can also look at the boundary now. So the next thing I want to say, if you look at the boundary of the knot trace, that's also called the 0 surgery. By K0. And that was actually studied much before. So what you do here, let's look at this picture here again. Now I remove the tubular neighborhood of the knot. I remove this dot from the boundary, solid torus, and I replace it by this other solid torus here and here. If I run to the boundary 3 and equal to this S3, I have removed the tubular neighborhood of a knot and replaced it by a solid torus in a different way. Yeah, so that's so here it's like this. It's the take S3, remove the interior of the tubular neighborhood, and then I glue with this gluing net phi a D2 times the remove a knot from a C-manifold from S3 and I glue it in a different way. And that was studied since then, like from the 1900s something. So I should maybe also say that the original Poincaré conjecture was just for homology. And the first counterexample was with such a surgery. I should say the first counterexample can be constructed with such a surgery. So that was what people did in three-manifold topology a very long time ago. And then later people also studied forming. And I should also say those manifolds I constructed here, this 0 surgery and the trace, these are like compact manifolds. And they're naturally oriented and have smooth structures. Yeah, and here again it looks like it's not smooth, there's a corner, that's true. But again, you can do this trick from before with the square. You can say this is homeomorphic to something smooth, and then there's a preferred smooth structure on that space. Whenever we say something like that, we mean the four manifold with this preferred smooth structure. Yeah, so let's maybe see one example at least. One maybe example where I can do it maybe by hand. Let's look at the trace of the unknot. Let's say this knot here we call U for unknot. And I want to look at the trace of the unknot. And I claim that D2 times S3. That's a pretty simple four-manifold because the knot is simple. And then the boundary is then S1 times S. Yeah, so the 0 surgery on the unknot is S1 times S3. And how do we see that? Yes, I'll try to explain it in detail. Yeah, W0 is a forward together with D2 times D2, glued with some doing that. And now the trick is to write the forward again as D2 times D2. Like this. And then we're just gluing two D2 times D2s together. And one has to analyze now how we do them together. Let me again draw this schematic picture. Okay. Yeah, so here I draw my D4. That's D3 times D3. And then I'm attaching a two-hander. D2 times D2. And then the picture gives us an idea that here you get actually an S2, and we have orthogonal to this or like the D2s, and this is in the structure of the trivial product, the trivial bundle, the D2 times S2. And how do we see that really? Yeah, so if we have now D4 written as D2 times D2, you can look at its boundary. D4 as then the boundary of D2 times D2 union D2 times the boundary. So I have decomposed the boundary of D4 S3 into two solid tori. And you see them here in the picture. Here's one, here, and the other is here, there, and there. So we have decomposed D4, boundary of D4 in two solid tori. And let's see color. And an unknot I see in there as the boundary of D2 times 0. And so here in the picture, and to the neighborhood of the unknot, here it was red. Del D2 times D3, which is this part. And this part. That's so one of this solid tori. And in the complement, you see the longitude. And the longitude sits here. And the longitude is del D2 times 1, which is the boundary of the disk. So this is this. Bounded by this. And because it's the boundary of the two manifold, it's null homologous in the first topology will not contain. And that tells you then that the product structures from here and here, they fit together along that longitude. And you can write it here. WU is the same as D2 times D2 D2 times D2. Then the product structures fit together, meaning that this is the same as D2 times D2 union D2, but this is an S2, so we get D2 times S2. And so this is the only example that you can really describe that easily. The reason is that the other examples, they don't have simple descriptions that I can write down for you. Their simple descriptions are just saying it's a not trace along a node. They don't have other names. But it's still a simple formula.
I mean, don't you have like some nodes that are like the bundles over S2, the non-trivial disk bundles over this S or something
And
like
yeah,
this?
if you do allow other slopes here, then you get all Euler numbers.
Okay.
So now if you imagine that this slope here is not trivial anymore,
Mhm.
then you get still a bundle, but it has non-trivial Euler number, and you can compute the Euler number is exactly the order is longitude. So nice exercise.
Okay.
But the topology of the results, can it be made as complicated as you want, or?
I mean, not because certain things are easy because it has a cell decomposition with the single two cell. So for example, it's simply connected. This second homology Z, but among those classes of manifolds, it can be pretty complicated. That's the reason why we can prove some of those exotic results.
And this one can also iterate these.
So exactly, you can also say, in some sense, if you generalize this construction, you get all smooth for manifolds. So you can say this was a simple example of a handle attachment, D2 times D2. But now I can attach any handle of any index I want, and then I get all smooth form flows. Does it make sense, though? So that's also one way to study the point-of-day conjecture. Write down a very complicated handle decomposition, show that this manifold is homeomorphic to S4, but not diffeomorphic. Maybe not the best way to do it. I mean, people tried that, and there were potential counterexamples around, but then always someone came up and showed that they're actually the standard S4. Yeah, are there other questions about tracing? Maybe let me state a few results that are known. As I said, somehow you want to understand when can I recover the knot from the form manifold. And in some simple situations, it is possible. In other situations, it's not possible. And so here are some results. And I mean, there are many more known. I just state some. Yeah, the first result I want to mention is that if K is one of these three simple knots that I just erased, and the unknot, the step point, or the figure 8 knot, then the following is known. If there is another knot, K prime, such that the zero surgery of K prime is the same as the zero surgery of K, the same, I mean, the demorphic, then the knots are isotopy. Then, of course, also the traces are the same. Yeah, so saying this result says that those three knots are determined by their trace. So if you just know the four-dimensional object, you can recover the knot. These are pretty hard results. And the unknot case is due to Gabay. That's also called property R. And the other two knots are due to Oswald and Sabo. They are pretty hard to prove. On the other hand, there are knots that are not determined by the trace. So there exist knots K and K prime that are not isotopic, such that their traces are determined. I think that was first proved by Eusener. He actually proved more. He proved that there are infinitely many knots that are all pairwise non-isotopic, but all have the same price. And I mean, this is quite hard. This is surprisingly easy once you see how it is. It's a clever trick. And once you see the trick, that's not too hard anymore. I won't tell you the trick. I mean, it's not that because you need some background in surgery theory, but once you have that, I can really write it down.
The first result is using these Fleur theories or what?
So the first result uses actually foliations.
Okay.
Figure biasing. And this uses figure homology and I think also instant homology. I'm not quite sure, but it uses gauge theory here. And this is foliation, so it's pretty hardcore mathematics. And, yeah, I think there are new proofs now of this unknot property R using symplectic topology also, but it's also difficult in some way. So I don't think there are easy proofs of those two ones. And here I also wouldn't say it's easy, but once you see it, it's kind of you bite yourself that you didn't see it yourself.
But can you, if you know that you have such a diffeomorphism, can you say something about K and K prime?
So there are certain things known. For example, if that many knot invariants are actually invariants of the trace. For example, the Alexander polynomial, the genus, the fiberedness status, the sliceness status, I will discuss it soon. There are many invariants that have to agree. But on the other hand, other invariants don't have to agree. So often you can distinguish those knots using hyperbolic volume on the complement. So that's how he distinguishes the infinitely many knots. So he has this infinite family, and he has a formula telling you what the volumes roughly are. From that you can deduce that the volumes are all different.
But you're having these WK and also the trace is the boundary. What does it have if the boundaries are isomorphic?
Yeah, great question. That's also known that there's a third thing that can happen. I think that's due to Boyer, I think. Due to Boyer. He proved that there are examples of knots that are not isotopic, such that their zero surfaces are the same. But their traces are not the same. That also is possible. Here I should say, I don't think one has infinitely many examples because those traces are distinguished by parity of the signature of some intersection form. There are just two. So I think here we only know examples where two are different. It would be interesting to have an infinite family. This is not known. So that was your question. Yeah, other questions about this? So okay, now we have this like for every knot, I can construct an interesting four manifold. And so then the question is, yeah, for which knots is this four manifold really interesting? And the answer is, if the knots has an interesting genus, then the trace is interesting. And what should that mean? So there are several versions of knot genera, and it should be chapter 3. We call slice knots. And yeah, there are three genera of knots. Yeah, the first one, the classical one, is the three genus. Three genus, or some people also call it cipher genus. It's the following definition. It's an integral invariant of the knot K. By G3 of K, and that's defined as the minimum value of the genus of the surface. So and such that the surface F sits smoothly in S3, such that and the surface should be connected, compact, and orientable, such that the boundary of the surface is not K. So I have an abstractly some surface which is orientable, and compact, and connected. So it looks like it and has one boundary component. Then it just is the diffeomorphism type of the surface is determined by the number of these rows. And this number is called genus. And then I ask for this minimal number for a knot. Yeah, so for the unknot, it's very easy. For this unknot picture here, I can fill it with this. Also there the genus is 0. And conversely, by my definition of unknot, everything is not the unknot has three genus bigger than 0. And so a knot has three genus 0, different only if the knot is isotropic. This is an unknot detector. And then one can ask, is this computable? Yeah, so for example, for this reference, you can do that. And I claim it's 1. And I guess it's best to see in this picture. And that's another diagram of the pattern. It's a homework to see that this is the same one as this, isotopic. And here I can really see the surface. And here some part. And then I make a twist here, go to the other side. And here with the rest of the circle. And then one can check that this surface is orientable. This genus 1, computing the Euler characteristic, for example. And because it's not the unknot, you believe that it cannot be 0, so it's 1. But then you see already it's like the difficulty in computing a genus. If I have a diagram, I can give an upper bound by finding such a surface. But then because it's defined as the minimum, it's hard to say when is it really minimizing. Nevertheless, it's computable. There are ways to 3 genus is a computable index. You give me an algorithm in the computer, I can tell you in finite time what is 3 genus.
What is 3 and 3 genus?
I mentioned 3. And maybe it gets more clear if I define the 4 genus now.
Okay.
Yeah, many people also drop this 3. If you read just G, people normally mean 3 genus. But I want to distinguish this here now. And maybe let me define the 4 genus and then I do a break. Okay.
Yeah.
So there are actually 2 versions of the 4 genus. The first is the smooth 4 genus, and the second the topological 4 genus. Smooth 4 genus. It's the following, very similar definition. I put the 4 here, and for smooth I put the C infinity here. And then I say it's the minimum genus among surfaces that now sit in Q4 and not in S3. That's the only difference, and the rest is the same. That's what I wanted to be smooth. I wanted to be compact, and connected, and orientable, and such that the boundary of that is the smooth 4 genus, and maybe that explains this reader. And then there is also the topological 4 genus. G for C0, okay? The same definition. Just that you now ask for this surface to be locally flat. And the rest is maybe I could explain the locally flat part after the break. And then we will see how this is different for genera, confused.
What does locally flat have to do with C0?
That's, I would say this means there's a topological embedding. And maybe let me explain it now. If you don't put locally flat here, if you just put C0, then every knot has smooth 4 genus, the topological 4 genus 0, because you can do the following thing. Take any knot, let's say it's that one here, and then I cone this off. And so I look at D4, the cone of S3, and in there I can cone the knot to some point here. This gives me a disk in the cone of S3, so it gives me a disk in D4. This disk is a topological submanifold. Then I have proven that every knot bounds C0 D2. But now you want locally flat, meaning that you have something like a local tubular neighborhood, which would not be the case here. And then the notion gets more interesting.
So it's something that falls anywhere automatically in the smooth case.
Yeah, the smooth embedding is
So we
locally
have to retain the topological fields in condition.
So somehow you want something like it has a tubular neighborhood. It's not quite correct, but I will write that down maybe after the break, the definition of locally flat. And then maybe it's a nice exercise to see that this doesn't work here. Then we will see that there are knots which have interesting 4 genus. Those notions differ, and it's not on this zero.
Is this sort of the same reason that like continuous knot theory doesn't exist? Like you can,
continuous knot theory exists, you can't just not say anything. It's a very interesting topic, you just have no results.
isn't it true that like everything just disappears because you can sort of,
Okay, you need the right notion of equivalence.
yeah, and that, but that's very similar to this locally flatness, I have a feeling.
Maybe, yeah, maybe. Yeah. No, I mean, the one other reason is we always restrict to smooth embeddings. If you just look at topological embeddings, even with the right notion of equivalence, you can't prove anything about it. For the right knots. That's the reason that there are no papers about that. Yeah, but let me stop you, maybe not. We continue.
Mark, you have the floor again.
Yeah, so we defined this three genus and the smooth genus and the topological genus. Maybe let me add the definition of locally flat. And so this first thought, we don't add a condition just by C0. It's a boring notion. Everything has minus 0. And if the F is locally flat condition, it's not true anymore. So what does that mean? It means more locally in the neighborhoods. So it means like here some manifold F and some ambient manifold before, let's say. Then it's locally flat. If we find for every point P in F, point P here, we find a tubular neighborhood, sorry, an open neighborhood U of T in F, something like that. And the neighborhood, let's call it V of T in P4 of the ambient space. Here, such that this pair is homomorphic. The pair U, B is homomorphic to B2, B4. So this picture here, homomorphic to the 2-ball B2 inside a standard or standardly embedded inside the 4. And so this is somehow meaning as a locally as a tubular name. And at this point here, this is not true. And so this embedding is not local. And so this doesn't prove that the trefoil has topological fault genus. And on the other hand, since every smooth embedding is locally flat, we know that corollary that G4 C0 of K is always smaller or equal to G4 C infinity of K. And since you can see a surface in S3 also has a surface in B4, this is also smaller or equal to this. Maybe it's more interesting that this is not always the same. But in general, it's not equal. In general, there are some cases where it's equal, in some cases where it's equal. Let me maybe spend the next few minutes explaining these examples or some examples where equality does not hold. So really it's explaining that this is an interesting notion. Here's one example for the first inequality. I draw a so-called ribbon knot. What is called the ribbon knot? Why is it called ribbon knot? Yeah, because it bounds very nice immersed disk. We try to draw in the disk here. Yellow. Here's the one part of the disk. And then I get here a self-intersection. And here I get another self-intersection along this line. The line of self-intersection. This is the line of self-intersection. And then it goes on. So this is an immersed disk in S3. And it has really nice singularities. Those singularities are called ribbon singularities, where you just have an arc that lies on one of the surface completely in the interior. And whenever you have such a ribbon knot, it is automatically slice. Slice means it's four genus, smooth four genus essential. So why is this? You can look at the neighborhood of this singularity arc in the surface where it lies in the interior. So something like that. Something like this here. And this. And then the only points where it's not an embedding is in the interior of this disk. And then what I can do is I can push this disk in the fourth dimension. And so it's exactly the same thing as if you have two lines crossing in R2. Then if you go to R3, then make one line going under the other. So here it was under, then I have made this into an embedding. The same I can do here. I can push this red part a bit down in the fourth dimension in a smooth way, such that this intersection is in four space recent. And then I have described, an embedding of the disk in D4 whose boundary is that node. So I've shown you that this node here has 4 genus 0. And now you should maybe, before I told you that the node has 3 genus 0 if and only if it's the node. And hopefully you agree that this is not the node. I won't prove that. In fact, it's the connected sum of two tuples. So I claim this is not the node, and you can do that by computing standard node invariance. And then you know that the 3 genus is not 0, and in fact it's 2. In particular, it's not. Okay. Does this make sense? And then on the other hand, you should maybe ask, are there nodes where the 4 genus is not 0 at all? And there are such nodes. The simplest example is the trapdoid. For the infinity of the trapdoid, this is actually 1. So it equals the 3 genus. That's meaning this is really an interesting notion. Yeah? It can be different and it can be equal to the 3 genus. And why is this? Yeah, so for showing that, again, it's like showing that something has a vanishing genus is easy. You just describe the construction, write down, find the diagram of this singularities, it's like. But if you don't find that diagram, it might be that you're just too stupid. And then you need some invariants showing you that you are actually not stupid. And there are certain invariants. Maybe the easiest one is the signature. And I won't explain the invariants. I will just briefly say where they come from. The signature, okay, actually the absolute value in one part of the signature is smaller than the topological coordinate. Then it's also a lower bound for the smooth coordinate. That's something that comes from algebraic topology. Easy to compute. And then there's more refined invariance actually for the smooth coordinates. Something like the tau invariant from Liga homology. It's the lower bound for G4 C infinity of K. That's like half gauge theory. Then there is the S invariant. In Liga in Cubano homology, yes, I think 1.5 of the S invariant. It's also the lower bound. Quantum topology. And there are also bounds coming from contact geometry. Maybe let me not write them because they are strictly weaker than those two bounds. But the point is, all those bounds are algorithmically computable. So if you give me a knot diagram which is not too complicated, something like this, you can easily compute it with a computer again. And then you have lower bounds for this. Yeah? So meaning if those invariants are non-zero, you know the knot is not this 4 genus and smoothly orthogonal.
But can you rule out the fact that there is a nice formula for G4 C infinity in terms of the others? We can prove that there is. Can you prove there is no such?
Probably you can give enough examples where the distance is very large. That, at least not in a very obvious way, I guess, that you can. I don't know, but I would say no. But, I need to think about it.
Can you also do something like saying, okay, I'm gonna look at the disk which is immersed there, and then do something with like the self intersections, but now they go to the boundary or something like
So
that?
I should say it's an open question. If the 4 genus is algorithmically computable. And I also say what I told you what to check is if a knot is ribbon. And what is called ribbon if it bounds a disk that has ribbon singularities. And it's one of the biggest open conjectures in low-dimensional topology, saying that every sliced knot is a ribbon knot. So it's there's no reason that a sliced disk should be of that form. So most people believe it's false, but there turned out to be true in all examples that people checked. And I mean, it's known that there are disks, slice disks for knots that are not ribbon, but then you can always find a different disk that is ribbon. So in all the examples that people studied, so I think those type of questions are all open. And
But I mean, here I'm not asking if it's ribbon or slice or something like this,
yeah,
right?
what do you think?
Well, so take a disk,
Yeah.
an immersed disk, maybe it doesn't exist, but in my head it does, whose boundary is the trefoil. It doesn't have these ribbon
Yeah, it has
singularities.
other singularities. Yeah.
It has other singularities, but there you can also not compute like, okay, it must have like an odd number of boundary, hit the thing in an odd number or something like this at the
I think
boundary.
so, no.
No.
Because then there would be an algorithm to check if something is sliced.
I'm not saying that you can fully compute it, but
Yeah,
give a
okay,
lower
yeah,
bound.
yeah. Yeah, I don't think so, but maybe there's a way to do it.
Okay.
At least I don't know. Yeah, so the only way to really prove that something is sliced explicitly is to find such a different disk, I guess. You would do exactly what you said. You start with an immersed disk and try to resolve the dead singularities by isotropies of the knot. Hoping it's just that it doesn't work on this thing. Does it make sense? Or?
Can you do a picture of like a singularity you don't like? For your
Oh, yeah,
immersive?
something like here's one part of the surface, and the other node, the other node goes through here, like this, and then the surface is here. And then you have the singularity. And the picture is not a bit, but I mean, like one part is this surface, and the other part is the surface going in this direction and intersecting here in such a line. And then you can still push this part here in the interior, but at the boundary it doesn't work anymore.
Yeah.
Okay, so this is a bad singularity. So maybe let me now explain that there are also knots where those two differ. That's much harder to show, and one uses a big black box for this. The example is, let me not write that, it's the positive white-hat double of the positive trefoil. And it's this, we draw a picture, and I'll explain this a bit. Here it's this. Here another twist. Yeah, so if you look from very far away in this picture, you just see a trefoil.
No, that's not true.
We need a bigger room. We're already going to discuss this, so that's.
If you just like look at these things, you see a trefoil, but then you see inside the trefoil, I put another knot. It's called the white-hat pattern, and then this is a general construction, and then one can show that this knot has 3 genus 1, I guess, and one can conclude it's Alexander polynomial. It's the knot invariant, a polynomial invariant, which comes from algebraic topology. And it turns out that whenever I do this construction, this white-hat double, in particular here, the polynomial is just trivial, it's just 1. And then, I'm not explaining what this is, but it's easy to compute. And then there's a deep result of Ripien telling you that such a knot with the Alexander polynomial is topologically sliced. So G4 C0 of K is 0. Proof is difficult. And then on the other hand, you can compute bounds like the tau invariant here, for example, works to show that this is not smoothly sliced. Tau, okay, it's non-zero. Tau, non-zero, and therefore it follows that P4 CQ2 is non-zero, it's actually 1 because the 3 genus is there. So an upper bound is. So this is less concrete, but
So, okay, say I don't believe you. And I just want to give the following argument why the C infinity thing is the same as the Z0 thing. It's like I start with my Z0 embedding or the flat thing. I just approximate it, which I can do. Why doesn't that work?
So what do? You approximate your C0 thing by C infinity thing?
Yes.
Why does there need to be a nice limit? Exactly what we go on.
No, but still, I mean, if I start with, like, I can definitely approximate it with an immersion.
Yeah.
But I mean, I'm 4 dimensions. If I started with something without self-intersections and then I approximate it, why would it suddenly get self-intersections?
On the genus, that's fine.
No, but I'm approximating the map.
But I mean, the map looks pretty flat in a, like a, by a homeomorphism, right? But
Mhm.
that is not, right? I mean, it's not a homeo. I mean, it's not like good for the smooth structure, right? So probably when you smooth out, I mean, the thing that looks super nice is smooth. Like,
I mean, I think
homeo
one
doesn't
should
look
just
very
not
nice smoothly.
try to think about this in such a way, because I mean that's exactly what's the weird thing is happening here. And that's exactly what will give you these weird results in forming for topology, that those things don't agree.
But they always seem to be like, okay, there's this deep result of Friedman,
Mhm.
which tells me that it's different.
Yes.
Okay.
I mean, at some point you need to use difficult mathematics to prove interesting things. So-
Maybe then I'm just comfortable proving not interesting things.
Yeah, I mean, I don't have a very good answer for this. And one of the reasons is like all these objects, these disks that are just topological embeddings, you can't describe them in nice ways. Otherwise, they would be smooth. Right? If there's like finitely many problems where it goes wrong, you can smoothen it in some way. So it needs to be some weird object that you can't describe in a finite process. That's the best answer I can give. Other questions? So okay, now we maybe partially, maybe at least we believe this, and maybe hopefully some of you believe this as well, that we have like knots where the topological cogenus and the smooth cogenus is different, and knots where the smooth cogenus and the smooth Z-genus are different. And then we can construct exotic R4s. This follows from the following 2 lemmas. Lemma A is the following, that the topological coordinates of the knot K is 0 if and only if the trace of the knot embeds into R plane. And with C0 I mean locally flat or local color neighbor. So it has something like a color neighbor. And lemma B is saying that the smooth cogenus is 0 if and only if the trace embeds smoothly. Yeah. Let me prove that. Proof of, let's start with maybe B. And I prove the backwards direction. So let's assume we have a knot K, with the knot trace smoothly embeds in R4. And I want to show that it's a slice knot, it bounces smoothly. So let's assume we have such a net F, and we write the knot trace as D4 together with the 2 random. And it was the definition. And then we can top that map such that this D4 is just the lower hemisphere in S4. Yeah, so I have here my S4. I have here my D minus 4, and here my D plus 4. I decompose my force here in two forwards. And I first homotopy such that this D4 is this D minus. And then the two handle is somewhere attached to. And the knot sits there. Now, if you're taking notes, it's getting easy because you can just turn your paper around. If you don't take notes, you need to make a handstand. And then you see that the knot is sliced. Because here, we look at the core of this handle. This D2. And this D2 is now the disk in this upper D4, whose boundary is the knot. It's a smoothly embedded disk. So the smooth genus of this knot, K, is vanishing. And so you just turn this picture, and then you see the smooth disk.
So you use here that the space of embeddings of the disk is contractible,
I use the disk theorem.
and you use also that the two handles are all.
No, the two handle is automatically it sits here somewhere in a very weird way inside. But in the middle of the two handle is
Oh, no, okay,
the
sure.
two handle is a D2
Okay.
times D2, and I just look at the midpoint to 0 times D2, and this core of this two handle.
Okay.
It might be, I mean, of course, in reality, it will be like knotted in a very complicated way. Just here in the picture, it seems. Yeah, so this implies that the smooth spot means okay. And by the way, the MIA works just the same, but it will need to work in the other category. Since we don't want to use this direction, actually, I won't prove it, but it's really the same thing. And let's prove the other direction in lemma A. This again is, if you stare at this picture, you see it again. Lemma A, the forward direction. And so let's assume that the core genus is vanishing. Then we know that there is it's locally flat. From that, we can deduce that there is actually a tubular neighborhood. And so there exists actually a D2 times D2 smoothly embedded into D4. And I see this D4 again as my D minus. Which here would be here my S4. I decompose it in D minus and D plus. And then I have this embedding here, this handle inside here. I mean, I already told you before. This is the handle. Let's turn this on. Yeah, so this embedding here, the boundary is the knot. Okay. And now you turn the picture upside down again, and you see a knot lace. This part here, D4, and this D4. Now, the only thing to check here is that the gluing here is really in such a way that that I identify with the longitude, which is null homologous. This is a small homology computation, and then you see that this is actually not traced with the correct longitude. Not too much. Just say this now embeds smoothly into S4. And then maybe here's I wrote a slightly different result. I wrote it embeds in R4, but since these are compact spaces, it's the same. Does this make sense? Right? Yeah, then maybe let's now prove this result that there exists exotic manifold, exotic R4s. Yeah, I claim that there exists the manifold M, smooth manifold, such that M is homomorphic to R4, but M is not differential. So it works like this. So I start with a not K. There, the topological 4 genus is vanishing, but the smooth 4 genus is non-vanishing. Okay, we subtract D4, C0, okay, it's 0, but D4, C infinity play is non-zero. Right, so it's topologically sliced, but not smooth. And one example would be this. And we know from lemma A, because it's smoothly sliced, the trace embeds into R4 as a topological embedding.
You said smoothly sliced, what do you mean?
Sorry, topologically sliced. So then we have a topological embedding. And so they exist in F from WK in F. And now you use that actually this is a color neighborhood. So the complement is again a manifold, topological manifold. And then there's this result that I told you before, stuff in words that if we have an open form manifold, we always find the smooth. So it's the result by Friedman and Quinn. It's again a result telling you that R4 minus the interior of the knot trace or the embedding of the knot trace is a smooth manifold. Or more precisely, it has a smooth structure. It's not a smooth manifold directly, but you can find some smooth structure. And yeah, the boundary of this manifold is homomorphic to the boundary of the knot trace. And then in dimension 3, you can isotope any homeomorphism to a diffeomorphism. Let's say this is B. And then we know that G is isotopic to a diffeomorphism, which calls BR. Yeah, so it's a map again from here to here, but now it's a diffeomorphism. And then you can use that map to glue those two spaces. And that's how this ends. So I look at R4 minus of the knot trace. And then I glue that to the knot trace. And not with the old map, but with this new diffeomorphism. This is now a smooth manifold. Because I glue two smooth manifolds with a diffeomorphism. And it's also homeomorphic to R4. Because the map G is isotopic to the old map. And if you glue with the old map, I just get R4. Yeah, so it's homeomorphic to R4, but it can't be diffeomorphic to R4 because WK does embed in that smoothly. And the smooth 4 genus is non-vanishing. That implies that this manifold M can't be diffeomorphic to R4. Using lemma B and backwards. And so whenever you have this kind of knots, you get exotic R4s. Does that make sense?
So these R4s that you get, they are sort of standard outside of the big ball.
Yes, yeah. So they're, I think they're also called small R4s. Because they're standard also. And there are also large ones. You don't get them with this construction. And also, I should mention, you don't get infinitely many also because you have no control at all with these results here, how this new structure looks like. Again, these results are some weird limit processes and no one knows really what goes on there completely.
But there may be.
I mean, there might be infinitely many, but I mean, also you would never get uncountably many because they're just countably many knots. But probably you can use this construction to construct infinitely many exotic R4s. But I mean, since this is not really a well-defined smooth structure here, because there are choices involved that you can't control, maybe it doesn't make too much sense.
You alluded to some universal exotic R4.
Yeah, I don't know exactly what that means. Maybe I shouldn't speak about it. Yeah, I can look that up if you want, but I just know that something like this exists, and I don't really know.
Which means that answer to my question that we know in detail.
Okay, so now we understand how to get exotic R4s. So, I guess maybe you remember that. We can also use these lemmas here to potentially construct exotic S4s. I mean, I'm saying potentially because no one knows how this really works, but
Sorry,
yeah.
the Friedman-Quinn thing. Okay, it says this is a smooth manifold outside.
No, it tells you there is this, you can
Smooth structure.
enroll this manifold with the smooth structure.
Yes. But like how not concrete is this?
Totally incomplete.
Okay.
Yeah.
No, but I mean, like I could imagine that they say, well, you choose like a sequence of points and then you do this, this, and this. That would still classify as concrete for me.
I didn't look at the proof in the detail that I can tell you something.
But this is also, I mean, this is you're saying in every open manifold, this is true. And this is some sort of handle by handle thing. Like you could say, like as long as there's no top handle, I can
Well, I
construct.
don't know, really, yeah. I mean, of course, you need also like the manifold to be connected and stuff like this. But I think it's true. But I don't know really how to mix it. But those proofs are normally quite complicated. Yeah, other question. Then let me now try to show you how to get exotic S4s potentially. I'll put the question mark here. And here's the theorem. I don't know really who proved it first, but it's well known somehow. If you have two knots, K and K prime, that have the same zero circle, meaning they are isomorphic, such that the four genus, the smooth four genus of K is vanishing, but the smooth four genus of K prime is non-vanishing. Then the Poincaré conjecture, the smooth Poincaré conjecture in dimension 4 is false. Yeah, maybe I should remark that, okay, we have seen that we can find knots that are sliced. We have seen that we can find knots that are non-sliced, computing this invariance. And we have seen that, I didn't show you, but I claim it's easy, can construct knots that share the same zero surgery. So you just need to make those three things together. And all this separate is always easy. And if you can combine that, you have disproven the Poincaré conjecture. Yeah, so let's explain the proof. So you construct, you can initialize before a manifold M using a trick with knot traces that is homomorphic to S4, but not diffeomorphic. So yeah, we know that K is sliced. So we can choose a slice disk. Okay. Select B, in before here 2 disk. Such that its boundary this is my before. Here's my not K. Boundary. And then I draw 2 disk. Might again be horribly knotted, but it's for easy picture. And then I look at the tubular neighborhood, this 2 disk. of V, and I remove it from V4. And so let's call this manifold EK for exterior. And it's defined to be V4 minus the tubular neighborhood of the, let's take the interior. Maybe let's take the. And yeah, then by construction, the boundary of this manifold, okay, is the zero surgery. And so why is this? So what have I done here? I construct the boundary. I removed the tubular neighborhood of K. Here. Okay. And replaced it by the complementary solid torus in the neighborhood of V. That was the surgery on K. Then one can again use homology to check that the framing here, the longitude, is really the correct one as the zero. Homology computation. So what I have done here is I have removed from S3 tubular neighborhood and then include them in solid torus in such a way that the framing is the zero frame. And then I define my manifold M as being the exterior of K and the knot trace of K prime, and I glue them together with this differential. I guess to get the orientations right, one needs to take here a minus this manifold and here minus the knot K prime. Maybe let's not worry about that. So you just glue those spaces together. And then I claim that this manifold here, computation in algebraic topology, it tells me that the fundamental group of this is trivial and that the homology groups are also trivial. For K equal 2 and so on. And so this is the right one company, and this is my Vitox basically. As a simple decomposition of this space, you know the homology of those spaces, and you compute the homology of the group space. And then this comes out. And then using Whitehead together with Gurevich, you get that M is homotopy equivalent to this one. And if you want, you can use Friedman to show that this is Riemann. Yeah, but it can't be diffeomorphic to S4, because then the knot K prime with these. How do you see this? So let's call a sketch again. Here is now the manifold M. And I have constructed it by taking a knot trace. This here. WK prime and gluing it to E of K. And then in WK prime, you see here the knot K prime. So in the other words, if you remove this disk here, this D4 up here, then the knot K prime bounds a disk in M minus D4. It smooths this. So it smoothly slices in M minus D4. Write that so K prime bounds the smooth disk in M minus 4. And then with this lemma that I erased, it can't be diffeomorphic. Since the smooth coordinates of K and K prime is non-zero. As soon as I have this three conditions together, it's wrong.
You say one more time what the first condition was?
And that the surgeries are diffeomorphic, the zero surgeries are diffeomorphic.
And that's a statement about,
Fully three-dimensional statement.
yeah.
And I mean, it just means that the boundaries of the traces are diffeomorphic. The traces, actually, I mean, it's known. My next remark is that if the traces are diffeomorphic, then the sliceness status of the two knots is the same. Four genus might be different, but if one knot is sliced and the other is sliced, and one knot is non-sliced and the other is also non-sliced. So if the traces are the same, that can't be true. But if just the surgeries are the same, it might be possible. Conversely, you could ask, is the sliceness an invariant of the zero surgery? That would prove that those construction always gives S.
But that's sort of the hard condition to check, because the one at the bottom is sort of,
No, I think this is those two are the hard ones. This is actually very easy. In fact, if you give me two knots, I mean, the second problem for swimming force is solved. So if you give me two knots, it is effectively solved. If you give me two knots into the computer, I can tell you very quickly if the zero surgeries are the same or not.
Okay.
And sometimes it's also easy to show those things. This is easy sometimes by finding the ribbon presentation. And this is sometimes easy by computing the right invariants and showing they are non-zero. But in general, it's unknown how to do that. And this is the complication.
so do you have like a computer running at home?
Yes,
Like just,
that's exactly the next thing I'm going to tell you. So, I mean, yeah, it's actually running at the moment.
that would be very spicy seminar if you solved it during the talk.
Yes, maybe let me, I mean, other questions? Okay, so maybe let me write these remarks here, some remarks that I just said. So first of all, the signature can't detect the non-vanishing. So the signature of K prime is always zero. Yeah, this is because the signature is invariant of the eraser that was here before. The signature is invariant of the topological proportionalist. And yeah, topologically, it bounds a disk. So the signature of K prime has to vanish. So the signature can't detect it. But the S invariant and the tau invariant might do it. Yeah? But the S invariant of K prime or the tau invariant of K prime might be non-trivial. And I mean, there is hope that this might actually be detected. I mean, Lisa Picarillo did some work showing that you can actually prove things with the S invariant about exotic manifolds. So there is hope that this is not completely crazy to believe that this might find such examples. And I also said before, if the traces are the same, if WK is the same as WK prime, then those are sliced or non-sliced, then then G4 of K is 0, if and only if G4 of K prime is 0. So we need to find an example where the traces are not the same. And I should also say that recently computers are good enough to compute the tau invariants and the S invariants for knots very quick, also if the knots have many crossings. So the tau invariance works on a normal laptop up to 100 crossings easily, and the S invariant maybe up to 50 roughly. And so I mean, this strategy is very old. And it was tried before in a paper called main and machine thinking about the four-dimensional point rate conjecture. And they exactly tried to construct such pairs where the S invariance detected. And at that time, computers were still very slow. They needed to use supercomputers. Now you can do it on a normal laptop. And maybe a year or 2 years back, Manolescu and Picarillo, they tried this. They had a systematic approach to construct such pairs. And they just computed. And some examples they couldn't answer it. I leave that as an open question, and maybe 2 months later, some PhD student Nakamura figured out that they don't give counter examples by rate conjecture. So the problem is really that you don't have potential examples. Yeah? So can easily construct such things, but in all examples you get like this either this agrees or this either zero or non-zero in both cases. So complexity is really to find the correct examples. And maybe let me, and then here maybe the idea is if there would be such an example, it should be simple in a certain way. Or if it could also be pessimistic and say if it's very complicated, then you would not find it anyway. So it's in both situations, it's very good to look at low cost, low complexity examples of knots. Okay. Maybe that's what we tried. There are two very natural complexity notions for knots that one could just try. The first one is the crossing number. And this is a multiplied CK. And it's just the minimal number of crossings in a regular number. In a regular number. So I take these diagrams that I was drawing before, and I count the number of crossings, and I do that over all diagrams, and then I take them in. It's not in value. And another maybe better, probably better complexity notion, the tetrahedral complex or triangulation complexity. We multiply T, okay. And this is the minimal number of tetrahedra. That are needed to ideally triangulate the knotted ideally triangulate S3 minus 1. So ideal triangulation is to take a triangulation space, remove the vertices, you get a non-compact space, and you get the knot exterior, call it an exterior triangulation of the knot exterior. And the minimal number of tetrahedra needed for that is this T. And these are two very natural complexity notions for knots. And then in their paper, Manrescu Picarilla, they constructed a pair where the crossing numbers added up is 26. 26. And you could ask if this is really the minimum, and that's what we proved. Okay. If you then with Nicholas Weiss, who's a PhD student in Berlin, and the result is this: the minimum number of dk plus dk prime such that k0 equals k prime 0, and the knots are not different, is 12. That's realized in a unique example. And for the crossing number, it's similar to that. And the minimal number of CK plus CK prime, where the surgeries are the same. This is 26, but that's not realized uniquely. It's realized by at least 3 pairs. Here I always consider knots, I only write one chirality. Yeah, so if K0 is diffeomorphic to K prime 0, then also the mirror of K, the zero surgery of the mirror of K is diffeomorphic to the zero surgery of the mirror of K prime. I don't list them twice.
Sorry, and the crucial property is that these knots are not the same.
They're not the same. Yeah, I didn't quote it.
Yeah, okay.
I mean, otherwise you can take the unknown.
Yeah, no.
And yeah, then you would hope, maybe hope that the knots that are simple, maybe before we find out such an example. And we didn't find such an example, and we can actually prove. I mean, what we do, how do we prove that? And the proof is very simple. Proof works like this. You know that the decision problem for 3 manifolds is solved. The decision problem for 3 manifolds is solved. Yeah, so that means if there is an algorithm that takes as input 2 3 manifolds, and then the output is diffeomorphic or not. And
What is the input?
the 3 manifold.
Yeah, but how?
I mean, maybe if you want that more precise, then any way you want. For example, the triangulation,
Okay.
surgery diagram, Picard splitting, any of those things. Anything that the computer can handle.
Yeah.
Yeah, I mean, mostly triangulations is the input, but then you can easily go to triangulation from all these other triangulations. And if you put in knot complements, you have the decision problems for knots also solved. Because the knot complement is a complete invariant for a knot. And therefore, this solves also the decision problems for knots. And yeah, that's the proof, right? Yeah, so what I then just do is I construct one example of different knots that share the same zero surgery. I compute this invariance. I have an upper bound, and then I can list all knots with, let's say we do the crossing number. And I have this upper bound 26. Then I list all knots up to crossing number 26. This is a finite set of knots, and I compare them. And I mean, the more amazing thing is that this is working, because like I think 20 knots, we have already 2 million knots. It was just done recently, and it was more like a computer. I mean, more like playing around with this known programs that this really works. And the thing is also that I mean the number of knot diagrams grows factorial, and the decision problem is also maybe not totally implemented even, but it's enough implemented that this was working. So we just check all possibilities and then check what is the minimum. Yeah, so in fact, we do more. Yeah? We create a whole census of knots that share the zero surgery up to a certain complexity. And then what we do next is we compute the 4 genus of all of them. That's in general not possible, but for those examples, we are managing to do it. And it turns out that the 4 genus was always the same. So that's that. And then you can try to do more clever things to search for such examples than just listing everything. Maybe I don't explain that now. Let's find this out. Maybe that's a good point to stop.